The objective of this lecture is to provide the basic mass properties of a rigid body. The starting point for this lecture is as follows. Let B be a rigid body with mass m, and let n be an inertial reference frame. And furthermore, let O be a point fixed in n, and let R be the position of a point fixed in B relative to point O. So in other words, we have a rigid body. This is what the picture looks like. Here's the rigid body. Call it B. We have an inertial frame. We'll denote this as N. And then we have a point O, and O is fixed in N. And then there's a point on the body. This is just an arbitrary point on the body, for which this position R is defined. So R, if you want to think of it this way, you can think of this point as being a point P on the body. And then this would be the position of P relative to O. So in this case we can say that let P be a point fixed in B, and let RP relative to O equal R be the position of P relative to O. Now, what we're going to do is we're going to define some quantities here that are going to describe the mass properties of the body. And the first one is going to be what's called the position of the center of mass. So the position of the center of mass of the body B, and again, this point is measured relative to point O. So measured relative to O, where O is fixed in the inertial frame N, is defined as, so we define it as follows. R bar, which is equal to, and we're going to define it as the integral over the body of R dm, all divided by m. Now, this integral, we have to be very careful with this. So where the integral over B is integrated over all mass points is the integral taken over all mass points, or all points fixed in B that have mass. All right, so that's the position of the center of mass. Now you can see that that position leads directly into two other definitions. So now we have the position of the center of mass. So next, the velocity of the center of mass is defined as the rate of change of the position of the center of mass in the inertial reference frame n. So in other words, we get the following result, which is that v bar n is equal to dr bar dt, which is going to equal the integral over the body of v n dm all divided by m. That's the velocity of the center of mass. Now, just to sort of make this even, let's like write this a little bit differently. We've got v bar n is equal to dr bar dt in n, which is equal to the integral over the body of vn dm, where again the integral is taken over all points in the body, fixed in the body that have mass. And so lastly, the acceleration of the center of mass in, say, of B in the inertial reference frame n is defined as the rate of change in n of the velocity of the center of mass, or I should say of the inertial velocity of the center of mass, which gives us the following, that a bar n is equal to d dt in n of v bar n, which is equal to the integral over the body of an dm all divided by m. Now, these quantities actually give us the mass properties of the center of mass. So we have now defined the properties of the center of mass of the rigid body B. And we can graphically sort of look at this as follows, is that we have an inertial frame N, and we have a point O that's fixed in N. And we have a body B out here, and there's a point on that body which I'm going to label C. That's the center of mass. Since we actually denote the position by a bar, it's not possible to actually write C, so we actually put it here, C. And this is the position of C relative to O, and that is equal to what we define to be R bar, where C is equal to the center of mass of the rigid body B. So now we have the position, and then the consequence of that is we have the velocity and the acceleration of the center of mass. So that's sort of the picture that we have of these mass properties. So now that provides information about the if you want to call it the kinematics of the center of mass, because we're dealing with that point that's defined through these integrals. Now the next thing we need to do is we need to describe the mass properties associated with the rotation of the body. So let's write this first down, which is that the mass properties of the center of mass of B provide information about the translation of a fundamental point on B fixed in B, I should say, that point being the center of mass. Now, we'll actually see this later, that this is an important point when it comes to kinetics of the body. But for right now, just leave it that we're interested in the center of mass in order to define the mass properties, and then we'll use it later on when we actually get into kinetics. But this is the starting point for the translation of a point on the body. Now, the next thing we're going to do is we're going to define what's called the angular momentum. This part is going to actually give us the rotational effect of the body. So this is angular momentum of a rigid body. And again, this falls under mass properties, but this time we're going to be dealing with rotation instead of translation. So the angular momentum of a rigid body B relative to an arbitrary point Q is defined as follows. So, this angular momentum, which I'm going to define as h sub q in n, is equal to the integral over the body of r minus rq crossed with vn minus vqn dm. Now, what's important here is, again, the integral is swept or taken across points fixed in B that have mass. Now, as a result of that, it means that every point when you integrate is such that it's fixed in the body, and but this point Q is not necessarily fixed in the body. So note that Q is not necessarily fixed in the body B. And that's because Q is an arbitrary point. Q is an arbitrary point. Now, the fundamental angular momentum that we're going to be dealing with in the study of rigid bodies is is the angular momentum of the center of mass. So the fundamental, and again, it goes along with the what we just did earlier, where we defined the properties of the center of mass. So the fundamental angular momentum for a rigid body is that measured relative to the center of mass of the body. And is given as h bar n, which is equal to the integral over the body of r minus r bar crossed with vn minus v bar n dm. Now, we have to make an observation here. Unlike the arbitrary point Q, so unlike the arbitrary point Q, the center of mass is fixed in the body B. So what does that mean? So as a result, the point on B, which is part of the integral, which is a point used to compute the integral, and the center of mass are both fixed in the body. And because they're both fixed in the body, we know that the velocity of that point minus the velocity of the center of mass is equal to the angular velocity of the body in the inertial frame crossed with the difference between the two positions. Now, let's look at this carefully. This last result comes from the first property of kinematics of a rigid body. So let's actually write this down so we recall. So recall this. Recall that for 2 points P and Q fixed in a rigid body B, the difference between the velocity of these 2 points in an arbitrary reference frame is equal to the angular velocity of the body as viewed by an observer in that arbitrary reference frame crossed with the difference between the two positions. So that's where I get this from. That's the first kinematic result for the difference between the velocity of 2 points on a rigid body. So as a result of this relationship that I have up above, so we then can write h bar in n as h bar in n is equal to the integral over the body of r minus r bar crossed with omega bn crossed with r minus r bar, where all I did was I substituted v minus v bar in n with omega bn crossed with r minus r bar. Now, let's actually use this result to our advantage in constructing a nicer expression for this angular momentum. In order to do that, let's let rho equal r minus r bar. So then, what do we have? We get that h bar is equal to the integral over the body of rho crossed with omega bn crossed with rho. And that is integrated over all points in the body. Now we can see in this last expression that a vector triple product is being integrated. Well, the vector triple product, so we can recall that the vector triple product A crossed with B crossed with C is, or can be, I should say, written as A crossed with B crossed with C is equal to A dotted with C times B minus A dotted with B times C. So now, using this result, we get the following. We can do the following. We can say that replace A with rho, replace B with omega Bn, and then replace C again with rho. So when we do that, we wind up with rho crossed with omega Bn crossed with rho is equal to rho dotted with rho times omega Bn minus rho dotted with omega Bn multiplied by rho. But now we can actually use the constructs that we developed when we developed tensors, and we can rearrange this last expression. So recall now the definition of the tensor product A circle cross B between two vectors A and B. What was that definition? That definition was A circle cross B when applied to a vector C, that's equal to B dotted with C times A. Now, as a result of that definition, we can actually use that in this last expression in the one over here, rho dotted with omega Bn times rho. So rho dotted with omega Bn, the whole thing multiplied by rho, is equal to rho circle cross rho operated on omega Bn. So therefore, we obtain that rho crossed with omega Bn crossed with rho is equal to rho dotted with rho times omega Bn minus rho circle cross rho operated on omega Bn. So now we can actually use another property which comes from the identity tensor. So also recall that the identity tensor which was defined as U has the property that when you apply U to a vector A, you get back A. So therefore, U, if I apply this to omega Bn, U applied to omega Bn is just equal to omega Bn. And from that, we can actually rewrite this vector triple product even further. We can write rho crossed with omega Bn crossed with rho is then equal to rho dotted with rho times the identity tensor dotted with omega Bn minus rho circle cross rho operated on omega Bn. So as a result, we can actually put all this into the angular momentum. So then the angular momentum relative to the center of mass is then equal to the integral of rho crossed with omega Bn crossed with rho, where the integral is taken over all points in the body. Well, that's equal to the integral over the body of rho dotted with rho times the identity tensor dotted with omega Bn minus rho circle cross rho dotted with omega Bn and then this whole thing is integrated over the mass points in the body. So we can maybe write that a little bit more neatly like this. H bar n is equal to the integral over the body of rho dotted with rho times the identity tensor operated on omega bn minus rho circle cross rho dotted with omega bn, and then this whole thing is integrated over the body. Now, notice that omega bn is a property of the entire body B and is not particular to any point on the body. So as a result, omega bn can be taken outside the integral to obtain the following result, that h bar n is equal to the integral over the body of rho dotted with rho times the identity tensor minus rho circle cross rho, and then this is integrated over the body, and then this whole thing is operated on omega bn. Now, let's go through a few things. So, we see that U is a tensor, and rho circle cross rho is a tensor. So that implies that rho dotted with rho, because rho dotted with rho is a scalar, multiplied by U minus rho circle cross rho is a tensor, which in turn implies that the integral over the body of rho dotted with rho times the identity tensor minus rho circle cross rho dm is also a tensor. So what we're going to do is we're going to say let I bar b equal the integral over the body of rho dotted with rho times the identity tensor minus rho circle cross rho, and this whole thing is going to be integrated over the body. This is what's called the moment of inertia tensor of the rigid body B. So as a result, we have that the angular momentum relative to the center of mass in the inertial frame of the body is equal to the moment of inertia tensor of the body multiplied by the angular velocity of the body B in the inertial frame. That is the angular momentum relative to the center of mass. So this is the angular momentum of B relative to the center of mass of B. Now what's useful about that? It means that when we compute the angular momentum relative to the center of mass, we get this nice structured result where it's always equal to the moment of inertia tensor multiplied by the angular velocity of the body in the inertial frame. Now, If we want to parameterize the angular momentum, we can do that. And we can actually do that nicely once we have this expression for h bar. Is that suppose now that E1, E2, E3 is a basis fixed in the body B. Furthermore, let the coordinate system with basis E1, E2, E3 have its origin at the center of mass of B, a point which is called C. It's the same point I used earlier. I defined it as C. Now, so then the vector rho can be expressed in the body fixed basis E1, E2, E3 as rho is equal to rho 1 E1 plus rho 2 E2 plus rho 3 E3. So now let's construct this quantity which we have here, which is this quantity rho dotted with rho times u minus rho circle cross rho. So this first thing tells us that rho dotted with rho is equal to rho 1 squared plus rho 2 squared plus rho 3 squared. Next, the identity tensor has the form the sum from I equals 1 to 3 of EI circle cross EI, which is equal to E1 circle cross E1 plus E2 circle cross E2 plus E3 circle cross E3. So this says that rho dotted with rho times the identity tensor is equal to rho 1 squared plus rho 2 squared plus rho 3 squared times the sum from I equals 1 to 3 of EI circle cross EI, which we could also write in another way, but is not really necessary for the purposes of this discussion. But this last step may actually be useful, which is that rho 1 squared plus rho 2 squared plus rho 3 squared, and then this whole thing gets multiplied by E1 circle cross E1 plus E2 circle cross E2 plus E3 circle cross E3. So next, we need to compute rho circle cross rho. Well, that's equal to the sum from I equals 1 to 3 of rho I EI, this whole thing, tensor product with the sum from I equals 1 to 3 of rho I EI, which is equal to rho 1 E1 plus rho 2 E2 plus rho 3 E3 circle cross rho 1 E1 plus rho 2 E2 plus rho 3 E3. Now this is the same thing we did when we did tensors. This is then going to equal the sum from I equals 1 to 3 of the sum from j equals 1 to 3 of rho I, rho j, EI, circle cross EJ. So now we can actually construct this this quantity rho dotted with rho times u minus rho circle cross rho. It's the difference between these two, but it might be easier actually to write this out in matrix form. So if we say let E equal E1, E2, E3, then what do we get? We get rho dotted with rho operated on U minus rho circle cross rho. This whole thing expressed in the basis E is going to equal this matrix. So let's be careful with this matrix. So if you look here, you'll see that there's rho 1 squared plus rho 2 squared plus rho 3 squared, and the terms are only the diagonal terms, E1 circle cross E1, E2 circle cross E2, and E3 circle cross E3. And then in these three diagonal elements, the first term in this rho circle cross rho term is going to be rho 1 E1 times a circle cross rho 1 E1, which is going to give rho 1 squared E1 circle cross E1. But there's rho 1 squared E1 circle cross E1 in the first term. So if I take the difference between them, I'm going to get rho 2 squared plus rho 3 squared in that first element. And then because the first terms, rho dotted with rho times u, only affect the diagonal elements, I'm going to wind up with minus rho 1, rho 2, and minus rho 1, rho 3 in the remainder of that first row. Similarly, when I get to the second row, I'm going to get minus rho 2, rho 1. And then, if you see here, rho dotted with rho times u, there's a rho 1 squared plus rho 2 squared plus rho 3 squared times E2 circle cross E2. And then in the rho circle cross rho term, I'm also going to get a rho 2 squared E2 circle cross E2. So that's going to give rho 1 squared plus rho 3 squared, and then minus rho 2, rho 3. And then similarly, I'm going to get minus rho 3, rho 1, minus rho 3, rho 2, and then rho 1 squared plus rho 2 squared. So now we actually have the all these terms, and now we're going to integrate each of these. So because I is a tensor, we can write the following. That I is equal to the sum from I equals 1 to 3 of the sum from j equals 1 to 3 of ij bar ei circle cross ej. Well, let's write this out in matrix form. So this means that I bar b, when expressed in this basis E, is going to equal the following. It's going to equal I11 bar, I12 bar, I13 bar, I21 bar, I22 bar, I23 bar, then I31 bar, I32 bar, I33 bar. That's the matrix that I'm going to wind up getting. Now, when you actually look at that matrix and you say, all right, well, let's relate it back to what we had earlier, which was in terms of these products with rho. What we can do is we can look and we can see that the terms inside the integral all have to get integrated now. So let's integrate them. So therefore, what are we going to get? We're going to get I11 is going to equal the integral over the body of rho 2 squared plus rho 3 squared dm. And then if we go through the next ones, we're going to get I22. These are the diagonal terms. It's going to be the integral over the body of rho 1 squared plus rho 3 squared dm. And then the last one is I3 3 bar is equal to the integral over the body of rho 1 squared plus rho 2 squared dm. And what we're going to wind up with then is we're going to wind up with those three quantities. And just to make this a little better, let's make this a little bit neater so that it's all in one line. I3 bar is equal to the integral over the body of rho 1 squared plus rho 2 squared dm. Now, those are these three diagonal terms that I have in this matrix. Next, we're going to notice the following thing. I12 bar is going to equal, well, let's look at this. It's minus the integral over the body of rho 1, rho 2, dm. But notice something. We'll notice that if you look at I21, it's equal to negative the integral of rho 2, rho 1. So this is also equal to I21 bar, because that, I'm going to put in parentheses here, is equal to the integral over the body of minus rho 2, rho 1 dm. Now let's look at I13. I13 bar is equal to negative the integral over the body of rho 1, rho 3 dm, which is also equal to I31 bar, which is equal to the integral, or negative the integral over the body of rho 3, rho 1 dm. So there we go. And now the last one is going to be I23 bar is equal to minus the integral over the body of rho 2, rho 3 dm, which is also equal to I32 bar, which is equal to the integral over the body of rho 3, with a negative sign, rho 3, rho 2 dm. So as a result of that, we can actually write this moment of inertia matrix, which is the matrix representation of this tensor in the basis E, as it's symmetric. We get I11, I22, I33, and then we get I12, I13, and then because these are the same, we get I12, and then I23, and then I13, and I23. Now, these quantities I sub I, for I equals 1, 2, and 3, are called the moments of inertia of the tensor I expressed in the body fixed basis E equals E1, E2, E3 relative to the center of mass of B. Next, the quantities I bar ij, and this is for I and j equals 1, 2, and 3, and I not equal to j, are called the products of inertia of the tensor I bar b expressed in the body fixed basis, should be a hyphen, body fixed basis, E equals E1, E2, E3 relative to the center of mass of B. So we've now written the tensor in terms of a body fixed coordinate system, and we've extracted from that 6 quantities. So there are 6 quantities here. They are the moments of inertia and the products of inertia. Notice that there are only 6 because the tensor is symmetric. So the moment of inertia tensor is symmetric. So that is that the tensor is equal to its transpose. And what that also means is that the tensor, when you write this out, transpose is also equal to the sum from I equals 1 to 3 of the sum from j equals 1 to 3 of ij bar ei circle cross ej, which is equal to I bar b because it's symmetric. Okay, so now we have the symmetric tensor. And again, we remind ourselves that the angular momentum relative to the center of mass in the inertial frame is equal to the moment of inertia tensor relative to the center of mass multiplied by the angular velocity of the body in the inertial frame. Now what we can do from here is we can actually relate the angular momentum of the center of mass to the angular momentum of point Q. So next, we can relate HQ in N to H bar in N as follows, which is that HQ in N, if we recall, was equal to the integral over the body of R minus RQ crossed with Vn minus Vq in N dm. But that can be written in the following way. R minus R bar plus R bar minus RQ crossed with Vn minus V bar N plus V bar N minus VQN dm, which can be written in the following four as the following 4 integrals added together. R minus R bar crossed with Vn minus V bar N dm plus the integral over the body of R minus R bar crossed with V bar N minus VQN dm plus the integral over the body of R bar minus RQ crossed with Vn minus V bar N dm plus the integral over the body of R bar minus RQ crossed with V bar minus VQ dm. Now let's look at these terms individually. So first, given how we defined the angular momentum relative to the center of mass, that first term is equal to the angular momentum relative to the center of mass. What about the second term? Let's look at the second term. The second term, the integral over the body, and look what we have here. We've got r minus r bar. So we've got r minus r bar. Let's look at this again. Crossed with v bar minus vq. So this gives us crossed with v bar minus vq n dm. But notice that the center of mass has nothing to do with it's a point fixed in the body, but we're not integrating over the center of mass, and we're not integrating over q. So this can be taken out of the integral, and we're going to get r minus r bar dm crossed with v bar n minus vqn. And that's because we're not integrating, we're integrating over points in the body, and the only thing that depends upon the particular point in the body is this position r. But notice that the integral of r minus r bar dm is equal to 0, so this whole thing collapses to 0. Also, we have that the integral over the body of, what's the next term? We've got r bar minus rq crossed with v in n minus v bar n, and that can be written in a manner kind of analogous to what we just wrote, which is the integral over the body of, we can factor it out again. We notice that r bar and rq are not dependent upon the integration of points over the body, so we get the integral of vn minus v bar n dm, and then in front we get the cross product of r bar minus rq, but the integral of v in n minus v bar in n, that's also equal to 0, so this last term, this third term is equal to 0. And then lastly, we obtain, what's the last term in here? We've got the integral of, over the body, of r bar minus rq crossed with v bar minus vq, which is equal to, well, everything comes out of this, and we're going to get, and then we're going to flip the sign on everything. So we're going to get rq minus r bar crossed with vq in n minus v bar in n. This whole thing is multiplied by the integral over the body of dm, but the integral over the body is equal to m, so this gives rq minus r bar crossed with m times vq in n minus v bar in n. So as a result, we can now relate the angular momentum relative to an arbitrary point q as being the angular momentum relative to the center of mass. That's the first term. The second and third terms were 0, and then we get plus rq minus r bar crossed with m times vq minus v bar. So what this tells us is once we have the angular momentum relative to the center of mass, we can compute the angular momentum relative to any other point on the body using this relationship. So let's write that down. This last relationship enables computing the angular momentum of a rigid body relative to an arbitrary point given the angular momentum of the body relative to the center of mass. So you can see here that the center of mass provides a lot of useful information. So in this lecture, we've been able to identify all the mass properties of a rigid body in terms of the center of mass. So let's summarize this. So summary. Mass properties of a rigid body. And this is really everything that one needs to know in order to be able to use the mass properties in problem solving. One is that the position of the center of mass is equal to the integral over the body of RdM divided by m. The velocity of the center of mass is equal to the rate of change in the inertial frame of the position of the center of mass. And then 3, the acceleration of the center of mass is equal to the rate of change in the inertial frame of the velocity of the center of mass in the inertial frame. Now this velocity of the center of mass is equal to the integral over the body of Vn dm divided by m. And then the acceleration of the center of mass is equal to the integral over all points in the body of the acceleration of all these points divided by m. Then we had this nice result for the angular momentum, which was that the angular momentum relative to the center of mass was equal to the moment of inertia tensor of the body multiplied by the angular velocity of the body in the inertial frame. And then we have this last result that tells us that the angular momentum relative to any point, an arbitrary point, is equal to the angular momentum relative to the center of mass plus RQ minus R bar crossed with M times VQ in N minus V bar in N. And those are the key mass properties for a rigid body. Now, on a final note, we can do this, although it doesn't really fundamentally change anything in terms of how this actually goes. But let's suppose that we want to do just this one thing, which is going to come up when we actually do the laws of mechanics, is that suppose that we want the angular momentum relative to an inertially fixed point. And I'm going to call that point O. Now, because O is inertially fixed, we can say, or we have, that the velocity of point O in the inertial frame is equal to 0, and the acceleration of point O in the inertial frame is also equal to 0. So as a result, suppose we let Q equal O. Then, because that last result is valid for an arbitrary point, I can arbitrarily set that point equal to an inertially fixed point, and we get HO in N is equal to H bar in N plus, well, what do we get? We get RO minus R bar, and then we get crossed with, well, VO is 0, so we get M times minus V bar in N, which gives us that HO in N is equal to H bar in N, and then we get plus. Now, when we do the cross product here, we're going to get a minus sign. We're going to get minus RO minus R bar crossed with M times V bar in N. Now, that's only true in this specific case where we're dealing with with the angular momentum relative to an inertially fixed point. In general, that's not going to be true. So recall, again, we're going to emphasize this. Emphasis, O is an inertially fixed point. If O is not an inertially fixed point, then this is not true. It's true if it's an inertially fixed point. But again, it provides us with a way of being able to move between the center of mass and an inertially fixed point. So you could kind of think of this as a last result, but it's really not a last result because the key result is actually the one that I have here in 5, which is that if the point happens to be inertially fixed, then we can just use this result and we can get the equation for an inertially fixed point. We really don't need to consider this as a special case of anything, but I did it just to be able to show you, because we are going to actually do the laws of mechanics using an inertially fixed point, and it's going to be useful to actually then to move to, once we've got the laws of mechanics for a rigid body, then we move to the center of mass. But we'll get into that a little bit later. Right now, we'll just leave it at this. So we've summarized these mass properties nicely on this page right here, and these are the mass properties that we're going to be using as we move forward with the with kinetics of a rigid body. And that's the end of this lecture.